Thank you, Eddie. Hi, I'm Zhang. So I'm a postdoc working at University of Maryland with Dr. Christine Hazel. So in this study, we are investigating the effect of dust turbocharging on the lunar exploration. So as discussed by Charles and many of others, that dust will be issued on the moon. And also it will be dealing with dust is very challenging, and especially when they are charged. So within the current considered charging mechanisms, the dust turbocharging is not receive less attention, but it could be a significant impact during the exploration activities by the robotic and human operations. So we want to look into this impact and evaluate its impact. And so first, we need to understand the mechanism behind this dust turbocharging and then quantify how much charging can accumulate on a dust particle. So, and as demonstrated in many of the laboratory experiments, that even with the identical insulator materials, when they are contact with each other, when the surface are separated, they can develop different kinds of polarity on the surface. So it's not well understood at all why even identical material can charge upon contact. And one of these hypotheses is that this could be due to some microscopic fluctuations on the surface of these identical materials. So one of these experiments, very interesting, carried out by Opataka et al. So they are looking into the amount of charges during the contact as a function of the contact area. And they found that for different kinds of material, when they are contact, the amount of exchange charge will be skewed with the area. However, for the same material, when they are contact with each other, the amount of exchange charge will actually skew with the square root of the contact area. So this will actually indicate that this contact electrification could be due to such a small scale difference. So imagine that on the material of an insulator, they will distribute it randomly. Some patch will be a donor and some other will be an acceptor. And only when a donor side is facing an acceptor side, their charge can be flowed from one particle to another particle. In that case, the charge flow direction will be randomly distributed on the contact surface, which will induce this square root scaling law. So our model is based on this idea. And so we visualize and model the particles in our model as such a patch-like feature. So some of these patches will be donor and some other will be acceptors. And so during contact, once a patch side with a donor and contact with another acceptor, the charge will be transferred from the donor to the acceptor. And in the real models, we will actually calculate the transfer probability based on the local electrostatic field. And then by sum up all the patches during the contact area, then we can calculate the total amount of transfer charges. And also in addition, in the model, we also take into account of the dielectric breakdown effect to correct the transfer charges. So here is the simulation that consider with a different kind of donor probability, which reveals some of the experiment's findings. And then further, we want to validate about how our model can predict the qualitatively the charging behavior of the dust particles, like in a sampling. And so first, the experiment we consider to compare is carried out in our lab, and which consider there's a shaking experiments carried out under vacuum. So there is the grain canister will contain multiple dust, like 100 micrometer size dust, and once it will be activated by the shaker, and it will become intensively charged, and then it will pass through electric field and images by the camera, which will be later analysis and provide the individual charges for each particles. So the result is showing in the left side, and the experiments have found that there is some polarity difference between the large and small particle population. Especially the small grains will tend to get a positive charge, and the large grain will tend to get a negative charge. So we implement these models, our turbocharging model in the DM code lights. And so this code, the DM code has been mentioned before. And now in addition to the mechanical interaction, we also consider the electric interaction and also the turbocharging mechanism. So this then we reproduce the experiments in the simulation. And as we can show here that we can like see by our eyes, the large particle get a negative charge and the small one get a positive charge. And by carrying out more analysis and comparison, and we have demonstrated that the simulation outcomes using this model actually can quantitatively reproduce the experimental finding in terms of the evolution of the bin charge and the time to reach the saturation state, as well as the overall charge distribution and their dependencies on the number of the saturation, the mass ratio of the large to small population. So when with this working mechanism, now we want to apply to study and understand how the dust can get charged during the lander plume. So we know that the lunar regolith will get heavily mobilized during the lander plume, and the particle can heavily collide with each other. And now we can study how much charge the particle can get. So since the DM simulation is very computationally expensive, so we only consider their using very small region of the lunar regolith, but we use the periodic condition to make our simulation more applicable to a real case. So we have modeled like millions of particles in such a small cell, and which contains like the particle size distribution as shown in this figure. And so it's about like 10 micrometer size. And then in order to reproduce, to get the plume density and velocity field, we get this result from the DSCMC calculations carried out by Cecily Sunday, and she will talk about that later. And so we just sampled the investigation site. We get the local velocity and density distribution of the plume field, and we applied into our simulations and to investigate how these plume interact with the dust particles on the lunar surface. And so here is a simulation we got, and the particles are colored by their charge level. So as we can see from this movie, that this particle can intensively charge during the lander plume. And we also compare the surface erosion rate with other study, and we found the similar, we predict similar erosion rate. And when we further move the investigation site away from the lander center, and we found that actually at like 10 meters away from the lander center, this charging effect is less important. However, close to the lander site, and when we analyze the individual particles charges, and we will find that very close to the surface, the charge of the particle is very intensive. And actually some of these particles, they will exceed the breakdown limit, and which may cause some dielectric breakdown effect and can facilitate the fragmentation of the dust particles under the plume interaction. So here is a takeaway from our study. So we developed, implemented, and demonstrate a working model for the turbocharging. And we also apply this to investigate the dust plume interactions. And we think the turbocharging could be an important effect that can need to be considered in the dust transportation with the plume. And we also think the dust turbocharging could lead to some dielectric breakdown event, which may explain some difference that has been observed before by comparing the images before and after the landing, which showing that the landing site gets smoother after the landing. So that's all. Thank you.